Hi everyone, this is Haoran Li. I'm from Cyber Physical System Laboratory in Washington University in St. Louis. Today's topic is about towards virtualization-agnostic latency for time-sensitive applications. Let's get into it. There are a lot of time-sensitive applications on cloud or edge cloud, such as the real-time streaming service Spark, or the in-memory database store Redis. Most of these services are consolidated or distributed on a virtualized multi-tenant platform. This is time-sensitive applications are not like traditional real-time ones, which addresses hard deadlines. For one thing, most of the use cases are not safety critical, and few deadline misses can be tolerated. Or for another, those applications, along with their runtime environment, are complicated. It is impractical to rely on worst-case bound, which is very pessimistic. But we also need to give some of timeliness for all these applications. So that's where the tail latency comes. And usually that is being referred to as service level objectives. In that sense, that just means like I want 90% tail latencies should be less than 10 milliseconds, and that should be a point on your latency distribution CDF. If that spot, so-called your SLO, is below your response time CDF curve, that means you just achieved that latency. It is important to maintain the same tail latency across different edge hosts when you're trying to deploy your service onto a shared platform. Our goal is try to achieve a consistent latency distribution for time-sensitive application on edge cloud. And the edge cloud will subject to CPU virtualization and the resource isolation policies, and we want to share the resource with general purpose applications without sacrifice the performance of these time-sensitive applications. So the question comes like how we can configure the virtual machine, control the response time distribution, and try to meet the target tail latency. So first, let me just give you some background of the real-time virtualization. Thanks to the real-time virtualization, we are able to consolidate multiple virtual machines within a physical host to just make the whole system more cost-effective and get a better utilization of all your physical resources. Each of the virtual machine is runtime isolated, and they will share the physical resources of the hardware. It employs some so-called hierarchical scheduling approach, where for each virtual machine, you got certain vCPUs. A hypervisor or virtual machine monitor will try to schedule the vCPUs onto the pCPUs, while within a virtual machine, the operating system or the application is responsible to schedule the tasks onto your vCPUs. In real-time scheduling, a vCPU is scheduled as a deferrable server, where each has a resource interface with two parameters, budget and period. Let me give you an example to introduce what a deferrable server is. Thinking about you have a periodic task running on a vCPU, and that vCPU will just occupy the full CPU. It's as if you just running that task directly on a physical CPU. So let's talk about this task has a period of 10. And has a execution time of 4 time unit. The schedule comes very simple. So when at time 0, the task releases the first job and executes for 4 time units, and at time 10, the task releases its second job, and you got it run till time 14. When running this thing on a vCPU scheduled as a deferrable server, the thing just changed. The deferrable server will got a resource interface which has 2 parameters, budget and period, for performance isolation. The deferrable server will consume budget when executing jobs. So for example, here we let the vCPU to be a deferrable server with a budget of 3 time unit and a period of 6 time unit. At the first 3 time unit starting from time 0, the task will just execute its jobs and steadily consuming the budget provided by the vCPU. While the vCPU exhausts its budget, the server started executing jobs. This is called budget enforcement. As a result, the task can no longer run when the budget enforcement happens. It can just cannot continue until the budget being replenished on next period of the vCPU. So you can see here at time unit 6, you will see the budget get replenished and the task continue to run. And this just causes a budget replenishment delay for the task due to the budget enforcement of the vCPU when running as a deferrable server. We deploy time-sensitive applications within a time-sensitive virtual machine, a virtualized host. People tend to dedicate PCPUs to the vCPUs of these machines. Says just like the vCPU to monopolize the PCPU to get the best performance of their time-sensitive applications. However, this approach will just cause over-provisioning. Can we just use a general-purpose virtual machine to try to reclaim the unused vCPU cycles from the PCPU and get a better CPU utilization without sacrificing the performance of your time-sensitive applications, so that we can preserve the latency distribution and still achieve the service level agreement for all these time-sensitive machines? Well, that's where we proposed our virtualization-agnostic scheduling approach. Basically, the idea and insights can be pretty simple. We just leverage the partitioned fixed priority scheduler in the hypervisor and let only one time-sensitive vCPUs per PCPU running at the highest priority per CPU. So in that sense, once your time-sensitive application wants to get some CPU cycles, since the vCPU gets the highest priority among the PCPU, it can always preempt the general-purpose ones and serves for your time-sensitive application. And it will also allow the work-conserving operating scheduler for the time-sensitive virtual machine. The deferrable server here for vCPU serves another important thing to perform resource isolation. Since the general-purpose virtual machine also wants to get some sort of resource to run the thing, they don't want to be starved by some misbehaved vCPUs. That's where you need to state a certain bandwidth or certain parameters for the resource interface of the vCPU and to just do a performance isolation. But the things doesn't come like that simple, because you also need to avoid budget enforcement for the conforming vCPUs. where you want to still achieve your virtualization-agnostic latency say always preserve the latency distribution of your time-sensitive applications. That means you should try to avoid the budget replenishment delay. So the question comes like this: how can you set the budget and period to avoid budget replenishment delay? Here we list the contributions of this work. We proposed the VAS, which is a scheduling approach for time-sensitive applications on virtualized host. It can preserve latency distribution for the time-sensitive applications and will require minimal bandwidth for the real-time vCPU. And it's got a simple resource provisioning policy. And we will show that later. And the VAS has also been implemented based on the Artisan scheduling framework. And we did the we will show the experimental results with both synthetic workloads and some real-time sensitive services. We have approved the theorem for the running periodic task set on our VAS system, where you got a periodic task set state as this, and you can compute the utilization of this task set by just get the summation of each of the execution time over their task period. And by knowing the task set parameters, you can simply get the resource interface of your vCPU like this. You just set the period of your vCPU to be the hyperperiod of your task set, which is the least common multiplier of all this Ti, and then setting your budget to be the period by the utilization. And by setting that, the vCPU can just avoid budget enforcement and achieve VEL without any provisioning, which means you just provide the bandwidth, CPU bandwidth the task set needed, since the bandwidth is equal to the utilization of the task. We also implemented our VAS based on the Artisan scheduling framework. The Artisan provides a scheduler called RTDS, which is Real-Time Deferrable Server Scheduler. It follows the deferrable server plus global earliest deadline first scheduling policy. So what we did is actually we created yet another scheduler called partition fixed priority scheduler, also leverage the deferrable server policy. So that's what we got for the VAS. So let's use our synthetic experiment to further understand what we should do with our VAS and how we can use our VAS to deliver the VAL for the time-sensitive task. Think about the first scenario, which you dedicated a pCPU to a vCPU to run in your periodic tasks, and the task set is just stated here. And we will use a work-conserving scheduler called the rate monotonic scheduler within the virtual machine to schedule the tasks. And on the other hand, we can also implement this thing with our VAS scheduling framework, which allows a non-CPU intensive general purpose workload running on a general purpose virtual machine, and to share the physical CPUs with the real-time virtual machine. And you can first compute the utilization of this task set, which is 76%. And you got the hyperperiod of all this task set, which is 2000 milliseconds. And by multiplying the period and the utilization, you got the budget. Now you just set your vCPU resource interface to be the budget equals to 1520 milliseconds, and setting the period to be 2000 milliseconds. And also setting the vCPU to be the highest priority. And then we can see the schedule. When running this task set on a full CPU, you can got this. This is a very typical rate monotonic preemptive rate monotonic schedule. And we got the trace on our VES, which just shows exactly the same thing. And the VES schedule of the task set can just on a shared CPU can approximate the one on a full CPU. And when showing the response time latency distribution, where the x-axis is the response time, while the y-axis is cumulative proportion of your latency samples. So you can just see for the full CPUs, it's just showed as a solid blue line, and our VAS it just totally overlapped with the distribution curve of a full CPU. So we can just tell that the latency distribution under VAS on a shared CPU approximates the one on a full CPU. Now let's just show some real-world case studies. So for the first case, we will try to use a Redis in-memory data scope as time-sensitive services, and we will use 6 client to periodically giving some queries to the Redis, and we know the period of each client to be 1 millisecond, and the execution time of each query is 0.12 millisecond. And based on that, we can got the utilization of 72%, and the period is just 1 millisecond, and you can also compute the budget. And setting that to our vCPU for the time-sensitive virtual machine, you can just run this service once on the full CPU and another on our VES, which shares the PCPU with a general purpose virtual machine. And you got the latency distribution, with the x-axis is the response time, y-axis is cumulative latent proportion of the latency samples. And you can just see our VES system can just maintain the same latency distribution as a full CPU, because you can see only very microsecond level differences here between two distributions. And another case study is involving Spark streaming. So it is well known that Spark streaming just used a micro-batched approach to rendering the incoming event, which means when your incoming event to Spark can be any pattern, but Spark will defer that and batch them based on some periodic time intervals, and this essentially renders your incoming event to be a periodic event. So the Spark just processes the incoming event periodically, and you can show a real-time trace of the one famous use case called the Yahoo streaming benchmark, and you can know that the period of the Spark application is just like 5 seconds here, and it's also running on a work-conserving scheduler based on a FIFO policy. And we built up yet another platform to evaluate this and showing how we can leverage this partitioned scheduling approach to support multiple platforms. So here we allowed 4 Spark workers, and each will have a micro batch of 5 seconds, and application window in this app is 1 second, and we will run that at 4 different that to 4 different pCPUs using partitioned fixed priority approach. And we can get the utilization of each of the vCPU or each of the Spark worker to be 75%, and the period just equals to the micro batch setting, which is 5 seconds. And based on that, you can derive what budget you need for your vCPU. And so you just set that to your vCPU, and we will run that thing on 2 different settings. One is on full CPU, just dedicate a pCPUs to the CPUs in the Spark virtual machine. Another is running that by sharing that with a general purpose virtual machine running CPU hog processes and sharing the pCPUs with the vCPU. And according to the cumulative distributed function of the 2 settings, you can just know we successfully approximated latency distribution on a full CPU, and yet just achieved our VAL. So we also maintain the same latency distribution as a full CPU for this case. So that just comes to our conclusion. So the time-sensitive service require consistent tail latency across different edge hosts. So we proposed the virtualization-agnostic latency, which is the VAL, is a required feature when you're trying to deploy your time-sensitive application across the edge host by simplifying the tail latency guarantees through consistent latency distributions. Yet we proposed virtualization-agnostic scheduling to achieve this goal on virtualized CPUs by allowing an application to maintain the latency distribution on shared CPUs, and also allows resource sharing with non-real-time CPUs, general purpose tasks. And we also demonstrate it is a practical implementation and a solution for some real-time use, real-world use cases, and we evaluate them for the time-sensitive service to see how our VAL system to be effectively achieve the VAL goal. And that's all I got for today. Thank you for your attention.